I'd like to start by thanking the organizers as well. It's a wonderful meeting. It's also a wonderful setting. You probably saw that many people did a lot of sports over the week. I benefited greatly from the scenery. I like it very much. I have a short title, What is New in Domain Decomposition? And to tell you what is new, because there are not so many experts in domain decomposition in the audience, I will start by telling you what is not new. So for this, it's best to look in the Bible. The Bible of Domain Decomposition is the book by Toselli and Widlund from 2005, 20 years ago. And there is a very interesting quote I would like to read with you. Domain decomposition generally refers to the splitting of a partial differential equation or an approximation thereof into coupled problems on smaller subdomains, forming a partition of the original domain. This decomposition may enter at the continuous level, where different physical models may be used in different regions, or at the discretization level, where it may be convenient to employ different approximation methods in different regions, or in the solution of the algebraic systems arising from the approximation of the partial differential equation. These three aspects are very often interconnected in practice. This monograph is entirely devoted to the third aspect of domain decomposition. So it's just to the linear algebra solve of systems. So that was the classical view, and that one is very well mastered. And a lot of work is based on definition 1.2, optimality. An iterative method for the solution of a linear system is said to be optimal if its rate of convergence to the exact solution is independent of the size of the system. So that's not new. And I'd like to give you the three main results. These are three seminal results in domain decomposition that are well established, and they basically summarize the main knowledge up to the appearance of this book. There are three types of domain decomposition methods. They're all on this slide. There are the Schwarz methods, there is the balancing Neumann-Neumann methods, and there is the two-level Feti-DP methods, if you want. And for all three, there is a theorem. And all theorems give a condition number estimate. So the first theorem for the Schwarz method gives a condition number estimate of a preconditioned operator that's bounded by a constant times 1 plus capital H over delta. Capital H is the size of the subdomains, delta is the overlap. So if this ratio remains constant, the condition number has a constant bound, so this is an optimal method. For the next method, the theorem says basically the same. If you divide by this S of UU, you get a conditional number estimate. It says it's bounded by a constant 1 plus a log of capital H over little h. Little h is the mesh size of your solver. Capital H is still the subdomain size. So if the ratio of capital H to little h is constant, this is an optimal method. And the third result is the two-level Feti methods result. You still have to divide by this quantity here to get the condition number estimate. It says constant times 1 plus a log, again h over h. So these are three optimal methods. Which one is better? Nobody knows. You cannot tell from this result. This constant here could be 1 billion, and this could be 1. It would take a long time for 1 billion to overtake 1, but it could never, because it's the same result. You have to, if this ratio is constant, then you're done. But these results are well mastered. These are results for Poisson time problems. Symmetric, positive, definite. And also nobody knows if these methods converge as an iteration. They're just used as a preconditioner. And none of these methods converges as an iteration. They all diverge. They can only be used as a preconditioner. If you iterate with these domain decomposition methods by subdomain solves, they all diverge. So this is not new. This is well known. So I'd like to start with things that are new in domain decomposition, where there is a lot of active research going on. The first thing is that I want to mention is Helmholtz problems, high-frequency wave propagation problems. All these results I've shown you are for Laplace type problems. So what's the difference between a Helmholtz problem and a Laplace problem? If you look at the operator, It's still a Laplacian. It's a change in the zero-order term, which is not even used to classify PDEs. To classify PDEs, use the highest order derivatives. So it seems to be a very small change. But it changes the solution and the properties of the solution fundamentally. If you have a Laplace problem, if omega is 0, omega is here the wave number, and if you ping the solution at the corner with a Dirichlet condition, then you get a solution that looks like this. If you add an omega, then the solution looks like this. Even though the matrix has only changed with a diagonal, nothing else has changed. Solution looks fundamentally different. If you look, iterative methods to solve such problem behave very differently. Here I use a GMRS on this problem. You get a good convergence. If you just add an omega, convergence is much, much worse. It's like 3 orders of magnitude worse. 3 orders of magnitude worse. It's much harder to solve this problem, much, much harder. And this is just the baby problem for time harmonic wave propagation. Maxwell is another one. Elasticity in frequency domain is another one. They're very important applications. So how can we solve such problems? Let's try with the Krylov method and the preconditioner. Let's take an algebraic preconditioner. Incomplete LU, for example. And here I use QMR because QMR is quite nice for these problems, in my experience. No theoretical basis, just my experience. But you see, if I increase this wave number, these methods struggle enormously to solve. If I put a preconditioner initially, it goes better, but then it goes worse. And even if you put an almost factorization, accuracy 10 to the minus 2, it just can't do it. And this is a small wave number, it's 20. It just doesn't work. If you use a multigrid method, similar problems. The wave number is increasing. Multigrid is usually used as a solver. You don't use it as a preconditioner. It's not even converging, it's diverging. If you use it as a precondition, and Krylov will help behind, but numbers go up drastically. Then in general, you would do more smoothing steps to get it better. And you go from divergent to stagnation, and you go worse with more smoothing steps. And then even more smoothing steps, you go better again. There is work by Aki Brand and Iro Lifshitz in 1997, where they devised a multigrid method that works for Helmholtz. I tried to prove it works, I couldn't do it. And now I know why I couldn't do it, because it does not work in a certain situation, which I will explain later. Then you can look at the Schwartz method. This is a really good method. You had seen this optimal condition number estimate for a Laplace problem. It's just diverging if the wave number increases. Here I have a little higher wave number. Schwartz is a powerful solver, but it cannot do this. As a preconditioner, it has increasing numbers. If the overlap is h, that was my delta, which is often in practice the size h or 2h. But I can also use a fixed overlap. I have an overlap that becomes more and more mesh points. And it still doesn't do it. It still doesn't do it. It does not work. Cannot use it. About 10 years ago, I wrote a review about this, and I tested all these methods, and I tried to explain why they don't work for these problems. They all really have a problem with Helmholtz operators. And then there was a new class of DD methods coming up in the community. And interestingly, it's not from the DD community. If you look at these people, none of these are core DD people. The first one was Enquist and Ying, sweeping precondition for the Helmholtz equation, moving perfectly matched layers. Then there was Cheng and Jiang, 2013, a source transfer domain decomposition method for the Helmholtz equation in unbounded domains. I met Jiming Chen at a conference in China, and I asked him why he came up with this method. And he said he could not understand this method. So it's completely differently written with Green's functions. This is written discretely with PML. Then there was a paper by Stolk, a rapidly converging domain decomposition method for the Helmholtz equation. Very interesting paper. There's the work by Laurent Desmanet and collaborators in 2018, nested domain decomposition with polarized traces. Ian Graham, Jan Spence, and John Jou wrote also a paper with impedance conditions. And all these papers are written in different type, different form, different notation, different mathematics. And we try to understand what they are and what they do, and they are all based on a common principle, which you find in optimized Schwartz methods. what they do, they still do classical Schwartz subdomain iterations with or without overlap, but they use different transmission conditions. And here I just write as an example. For a Helmholtz problem, on a rectangle, two subdomains omega 1, omega 2, they overlap. A classical alternating Schwartz method would just solve the Helmholtz problem on the left domain and then use this data to give it at the interface to the right subdomain, solve there, then use this data, give it at the interface here to the first subdomain and solve alternatingly. There's no Krylov method in this Schwartz method. It's just a subdomain solve iteration. And the main difference of optimized Schwartz method is that there is an operator here. The classical Schwartz method exchanges Dirichlet values, traces of the solution, and these methods exchange normal derivatives plus an operator applied to U. This could just be a constant and it would be a Robin condition. Could be an integral operator, could be a PML, any of these structures. And if you use this formalism, you can derive all the methods that were on the previous slide. They all function like this. They can all be written mathematically like this. But I had proved for these methods that they're also not good for Helmholtz problems over 20 years ago. I wrote a paper with Frederick Nataf, and I showed convergence deteriorates like omega to the minus 1 over 4. So the contraction factor goes towards 1. And I was convinced there must be an error in all this work because it's just not possible. He's had proved it doesn't work for two subdomains. So how can I work on many subdomains and show it works? And I only realized last year what the real point is, and that's my first point I want to explain in my talk. So here I show you the same solution we've seen before. That's the Helmholtz equation where you ping here at the corner, and it was a cavity problem. So I have Dirichlet conditions, like for Laplace's problem. It's in a cave, the equation, and then it oscillates like this. And now I make this into a waveguide. So I change the problem. It's a different physical problem that only has two walls and two open sides. And we look at the solution. It looks different. It still oscillates quite a bit. So there is now a wall here, a wall here. You start to see the ping at the end here. It still oscillates. It's in a waveguide. And now I will make this into a free space problem, which means I have absorbing boundary conditions all around, different physical problem. And then the solution looks like this. And what I found out is these problems here, they are as easy to solve as Laplace's equation with domain decomposition methods. And I can prove this. And all the tests on these new methods were done on such problems, not on cavity problems. So it's not just the operator that makes this difficult. It's not just the time harmonic operator. It is with the difficult boundary conditions that it's hard to solve. And that's my first important message. If you ever touch equations like this, if you have open boundaries, you're going to be able to solve this well with an iterative method. And if you're in a cavity, open cavity waveguide, it's going to be very, very, very difficult. It's very difficult to solve. So I wrote a review in Acta Numerica about this, where we describe this investigation. And it's almost an encyclopedia. You find for virtually every problem that you can think of with every type of boundary condition, what Schwartz methods of these sweeping types with different organization of your subdomains can give you as performance, and it tells you when it will work and when it will not work. So if you have to solve such a problem, it's good to go there, look, find your situation, and it will tell you, give up, use a direct solver, or use this type of method and it will work. So that's the first thing I wanted to say. The second thing I wanted to say is about scalability and core spaces. And I go again to the Bible, Toselli and Widlund, in the classical view of DD. Therefore, an iterative method for the solution of the resulting linear system in which information is only exchanged between neighboring subregions must necessarily, for certain initial errors, require a number of steps which is at least equal to the diameter of the dual graph corresponding to the subdomain partition. In section 5.4, we then consider the problems of devising efficient core solvers, which are the key and quite delicate part of any successful preconditions for three-dimensional problems. So you need a core space, and this is well accepted in our community. If you have many subdomains, you need a mechanism to propagate global information. Otherwise, you cannot be optimal. So here I will look at two types of decompositions. This is a square decomposed into small subsquares. And because I want overlapping subdomains, I start with a non-overlapping decomposition in the blue omega ij tilde, and then I just enlarge them. That's how I can create an overlapping decomposition. And here I do the same, but this is a strip decomposition. This is the one sees in these sweeping solvers. You sweep across the domain and then go back. So these are two different decompositions of a domain. And there is a first interesting fact that is also not known for so long. Actually, you don't always need a core space. Even if your diameter grows, you don't always need a core space. And this is a typical example. If I have a one-level Schwartz method that uses two subdomains like this, or it uses 3 subdomains, or 4 subdomains, 5, 6, 7, 8 subdomains, this is perfectly scalable with a one-level Schwartz method. And now you should say, what? That doesn't make any sense for a Laplace problem, because this is, if you have a source here, the solution here depends on the Green's function is non-local. And again, it's the boundary conditions that make this scalable. If you have a Dirichlet boundary condition all around here, this is perfectly scalable. If you have a Neumann condition, it's not, you need a core space. It's again the boundary condition that changes it. And the way this was discovered, there were molecular simulations done in a solvent model. And it was discovered that you can add atoms to your molecule and make it longer and longer. And the Schwartz method that uses the subdomain, the atoms, was scalable. And this can be proved rigorously with all DD techniques that exist. We wrote 3 papers about this. Such geometry is scalable. This geometry is scalable because there are holes. There is solvent in here, because there is a Dirichlet boundary condition there. This is scalable. They're all scalable. As soon as there is no hole, you're not scalable. And this holds for any domain decomposition method. Also, the other FETI, every other method is scalable on this geometry. Just one level. But if these holes are not present, then you're not scalable. And there has been a lot of research. Nicole Spillon has contributed tremendously to this field for core spaces. And I just want to show you what the latest thing is that we start to understand. If you look at such a decomposition where we decompose a square into, like, say, 8 by 8 subdomains, we run a Schwartz method on this, and we look in the spectrum which are the modes that converge the most slowly. It's for a Laplace problem. Then the first mode, the most slowly convergent mode, is an eigenmode of the Laplacian. But it just looks like an eigenmode. If I look at the second mode, which has the same eigenvalue but with negative sign, you get the same shape, but now you get piecewise your subdomains, and the function is harmonic on each subdomain. So these are the 2 most slowly convergent modes. Then the next slower mode is this one, and by symmetry there is also the mode turned. And again you have 2 discontinuous modes like this, where you can see the subdomains. And when I saw these figures, I immediately thought about the book of Hack-Busch on multigrid. If you've ever looked at multigrid in 1D, and you use Jacobi as a smoother, then you have the slowest mode, the sine mode, which converges as the slowest, and you have the highly most oscillating mode that also converges the slowest. And that's why in multigrid, if you use Jacobi as a smoother, you need a damping parameter. 2/3 is the best choice. 1/2 is often chosen as well. And now you see the Schwartz method does exactly the same. It's a block Jacobi method. And you see not the points that oscillate, but the subdomains that oscillate. And the functions in the error are all harmonic on the subdomains. So this is not really the first eigenmode. It's harmonic patched together with the subdomains. So these are the slowest modes. So if you want to use a 2-level method, you should have a relaxation parameter to get rid of all this. And then you get a method that converges as well as multigrid. You do not need Krylov acceleration for this. And here is an example. So these are all Schwartz methods. This is a classical Schwartz method, 2-level, with a 0 algebraic overlap, which means 1 mesh size overlap. And here is the number of subdomains. It's a scaling experiment on a parallel computer. Here is computation time in seconds. The calculations were done by Serge van Kriekingen. And these are all optimal methods. These are all optimal methods, you can see. They're all scalable. So I don't use the word optimal anymore. I say scalable now. Because this method is much less optimal than this method. And this method is even less optimal than this method. But I also put a multigrid solver here from the PETSI package. And this is the first time that there was a Schwartz solver that converges better than multigrid on a Poisson problem on a parallel machine. It takes a lot of things to do it. And the way to get there is these ORAS methods. They use the same optimized transmission conditions that were developed for the Helmholtz problem, but now optimized for a Laplace problem. Then you get with a Schwartz method to this type of performance. And there is no Kraloff acceleration. This is a basic solver. It uses all the power of a Schwartz solver to get there. Then I have a last new thing I want to show you. It's decompositions in space-time of evolution problems. So it's time parallelization, pint, parallel in time. It's not pint, it's pint. And the time direction is special. So I just take a very small problem. I take an ODE with an initial condition. And to tell you why this seems difficult, I discretize by an Euler stepping method. So if I know U0, the initial condition, I can calculate an approximation of U1 with this recurrence relation. And then once I know U1, I can do U2. And then I can do U3. And then I can do U4, 5, 6, 7, up to 12. Completely sequential process. And what one wants to do in pint is one wants to solve this in parallel. And if you want to do domain decomposition for this method, you decompose this problem into 3 subdomains in time. And you want to calculate here at the same time as here, at the same time as here. And that really doesn't make any sense. So when you start to work in this field, you have the feeling, I mean, this is just nonsense. How could you do any reasonable calculation at U9 to 12 before knowing what this trajectory does? And pint methods do this. Pint methods do exactly this. And now I want to explain to you why it works for certain problems and why this will not work for other problems. So I take a heat equation. A heat equation in 1D, ut equals uxx. I have the x-axis here. I have the time axis here. And I put the source F, and I just put the heating device. So I heat here. It's like a bar. And it becomes warm. Then I turn off the heater. It cools down. I turn on again. I turn off. Turn on again. Turn off. This is exactly a problem of that time-stepping nature. Nevertheless, this solution here I can calculate without knowing what happened here. It's like I can predict the temperature in your living room in February 27th next year. I just need to know if your windows are closed and if your heater is on. It doesn't matter how many parties you have until Christmas. All this is forgotten by the equation. This you can solve perfectly nicely in parallel. You don't need a core space. Same reason like for the molecular problem. It's the boundary condition and the source that determine the solution locally. This is local in time, even though it's the far future. This changes if you put Neumann conditions. Here I put Neumann conditions. Now if you heat here, then you turn it off. The whole thing is a bit warmer because it's insulated. It remembers that it was heated. So if a little later you heat more, if it's perfectly insulated, it remembers it was heated. So now suddenly the solution here depends on if you turned on the heater here or not. So this will need a mechanism that propagates information in time. But it's very low frequency information. It's very simple to represent. It's a constant in this example. So you need a mechanism for low frequency, and it's going to work very well for this type of problem. This is an advection equation with the same source. It's a transport going from the left to the right. So you transport from the left to the right, same source. It goes out of the pipe. It leaves the pipe. You put some more dye in, it goes out. Some more dye in, it goes out. This is the equation ut plus ux equals f. What happens if you put periodic boundary conditions? Then all hell breaks loose in this problem. Because the solution that goes out here comes back in, goes out here, comes back in, goes out here, comes back in, goes out here. If I change this profile by an epsilon, at the end here, it's going to change by the same epsilon. This is a hyperbolic problem. This is going to be very difficult to parallelize in time. It does not forget anything. So this needs very different techniques to be parallelized. So I show you a first algorithm that works very well for parabolic problems. This is the parareal algorithm. It's It's a very simple algorithm. You take a system of ODEs, you decompose the time interval into subdomains in time, and you do a correction iteration. You need two solvers, a G, which is a coarse solver that solves for an initial condition at time t1, gives you a solution at time t2. You have a fine solver that does exactly the same, but with much more accuracy, and you just perform this correction iteration. So you take a combination of fine solves, which you can do. K is the iteration number here, n is the time point. All these you can do in parallel, and there is some correction with coarse, which is sequential but cheap. Was invented by Lyons, Made and Turinici, résolution de dp par un schéma en temps parallèle. How does that work for my heat equation? Now I actually heat and cool a little more, so we have a little more signal. So I heat, cool, heat, cool, heat, cool. Here you see the first iteration of parareal. Here is the error. The error is order 1. Now I do one correction. Now the error is order 0.1. Second iteration, 0.01. I gain a factor 10 in each iteration. Converges very fast. You also see another mechanism. There is a finite step convergence happening in this algorithm as well. So here it works extremely well. Now we take the advection problem. Same algorithm with periodic conditions. And you look, error is order 1, order 1, order 1, order 1, order 1. No contraction whatsoever. Cannot use this for a hyperbolic problem. It's just not working. It's not the right method. But there are even much better methods for parabolic problems in space-time. This is a space-time multigrid method. This really uses the fact that you have access to the code, so it's an intrusive method, and it converges tremendously well. This is a weak scaling experiment where we have more and more cores, a larger and larger problem proportionally. Iteration numbers are 7 iterations. Time is 30 seconds to solution, and this is the best parallel implementation of a time-stepping method using a multigrid parallelized method to do the time steps in space. There's no chance to get to times like this. This is just not possible. This is the best solver for parallel problems in space-time currently. It's better than the decomposition method parareal. It's much faster. What do you do for a hyperbolic problem? You need a different method, different decomposition. And there was a decomposition invented by Gopalakrishnan, Schöberl, and Wintersteiger in 2017. It's called mapped tent pitching. And this uses all the feature of hyperbolic problems to work. What they do is they start at the initial condition and they pitch tents. And because it's a hyperbolic problem, the propagation speed is finite. And so in each tent, you can calculate the solution without knowing what all the other tents do, because information in hyperbolic problems is local. Once you have the solution in all these tents, you pitch new tents. And you do the same again, and you pitch new tents. This is the best Maxwell in time solver currently, which is space-time parallel. But it has 2 flaws. One flaw is to solve in the tents. They use a mapping to get into a cylindrical domain to do time stepping, normal time stepping, and then map back. And in this process, the normal time stepping has order reduction. But they're very good mathematicians, not only very good coders. And they developed methods that do not have order reduction. And when I was in a talk a summer a year ago, I realized there's a different way to code this method to get rid of all these problems. And there we do real domain decomposition in space-time. So here is a decomposition into 5 subdomains. There are red domains, omega 1, 3, 5. And there are black domains, which are fully overlapping with the red domains. And here is a cartoon where I have like space and time. And I solve in space-time domains. So these red domains are in space, but they're also in time. And I solve in parallel, and it's a wave equation. And so I get the exact solution in these tents, and I get garbage outside here if I start with random boundary values, because I don't know what the solution is. And then I march. Now I do the black subdomains, and the red subdomains, and the black subdomains, and the red subdomains. This algorithm doesn't know anything about this tent pitching. It just does the subdomain solves. But if you run the algorithm, like in this wave equation example, then you see the algorithm constructs these tents without knowing about it. It just forms these tents. And it has the same convergence properties like tent pitching, map tent pitching. It's very easy to code. This is the entire code. I coded this in an afternoon using restricted additive Schwartz technology from domain decomposition. I'm ready. There is a last example I want to show you, which is this transport equation that it works so badly with parareal. It's a different method. It's called paradiag. I will not explain it to you, but just look how fast it converges. Error is order 1. Error is order 10 to the minus 3. Error is order 10 to the minus 6. Error is order 10 to the minus 9. And this is also fully parallel in time. So there are many of these methods. But without going through a summary, I just would like to say for as a conclusion, I finished a book about this time parallelization. It's this book here. It's appearing in Siam now. And you find everything about time parallelization that's known up to today in this book. And the book is written in a style where you have historical introduction to all the methods, you have a full convergence analysis, and you have a runnable code in the book. And I'm working on a similar book for domain decomposition. It was a book that will go to CERN. I hope it's going to be finished next year. And I'm a bit old-fashioned. I still write books. Virtually nobody writes books anymore, but I like writing books. So there's one on iterative methods for linear systems, preconditioning, and also one for numerical PDs. So if you like books like this, please take a look. Thanks a lot.
Thanks very much, Martin. Question? So I have a quick question back on the scalability. So when you had these domains like in a grid, you said it depends on, you had to have holes. So does it depend on the size of those holes?
It's robust in the size. As long as you have holes, it's going to pin down your solution there and it's scalable. It's going to be slower in the size of the holes, but it's going to be scalable. So you have an upper bound with a constant. But it's going to be slower. But it will remain scalable as long as you have holes. It's good.
Any other questions? Okay, so let's thank Martin again. So thank you, Martin.